Today we're going to go over Module 8, Asynchronous Learning. This is our last module, and here we're going to be covering Regression Discontinuity Design, also known as RDD. And for this section, we're going to actually be replicating a paper that we discussed briefly in lecture and also in the asynchronous learning slides. I suggest to look over those slides before you go through the code here to get better context. But just to give you a rundown on the paper, it's the Lee, Moretti, and Butler paper that's looking at how much of an impact voters have on electing politicians. So just to sum up the paper, basically in the beginning they introduced this Downsian paradigm that basically suggests that politicians are going to strategically play a median voter strategy, which, if you remember from game theory, is just the idea that if there's two politicians and they want to get the most votes from all of the voter share, they're both going to place their campaigns or their ideologies, their beliefs, whatever it may be, in the middle. So they're going to moderate their ideologies to meet in the middle so that they can grasp on both to the left and to the right as many votes as possible. And so since this has been kind of our theoretical framework utilized in game theory, as well as an understanding of politicians, elections, these kinds of strategic decisions, this paper actually wants to determine in an empirical way and a causal framework whether voters are able to make the Democratic and Republican parties that have typically opposing viewpoints have a convergence. So basically in this paper they're testing, do we see a convergence in ideologies and for the politicians to gain the most voter share on both the left and the right, or do we see a complete divergence in political ideologies? So instead, on their policies, they're not going to, change their viewpoints to moderate one another or to be in the middle, yet they're going to stick with their original, maybe very left or very right viewpoints. And so the way the paper frames this problem contextually is they want to empirically test whether voters affect or elect candidates. So in this framework, if a voter or if the voter share in an location is able to affect a politician's ideologies, that means that we should exhibit convergence, meaning we should find the median voter theorem. Both the Democratic and Republican ideologies and policies should fall at the middle. But, and that would be the Downsian paradigm. But if if voters don't affect but rather elect politicians, that would be the case where we see opposing viewpoints, such as a divergence in political ideologies, meaning politicians will stay to their party's rhetoric and prior beliefs historically, whether it be leaning to the left or to the right, and stay to that side or that end of the spectrum. They're not going to attempt to moderate their policies to be in the middle. So this is a very important question. Of course, if you guys have been following politics recently, it's very interesting to see how voters play into different politicians' platforms. And so this is a very topical paper, even though this was published a while ago in 2004. So another thing is their data is coming from the 1960s up until the late 90s, so mid 90s to late 90s. So that's something to also keep in mind when looking at these results. But let's go ahead and get started here and try to see if we can replicate some of the tables, the figures. Some of these figures are going to be a little bit different, but and then the ones that they present in the paper. But I'll kind of explain as we go through what the meaning of each of these are. So first, let's set our working directory and load in the data. So if we look at the data, you have the state name, what district it was, incumbency, so meaning who held the prior seat, right? So was it a Republican turning to a Democrat, Democrat to a Republican? So it's important to know who held the seat at the time of the vote. And then you have this Democratic voter share, Republican vote, the year that the vote happened, the Congress. You have a bunch of these different different variables. You have the name of the person, the office, the party. Another important variable that we're going to be looking at is this ADA voter score. And so that's something that's also discussed in the paper. So this is a liberal group, and they basically determine how liberal a candidate is based on some scoring mechanism that they create based and comparing the beliefs and platforms of other politicians that are running. And so we can see here this person got 100, and so they are going to be scoring more liberal, and they're actually trying to beat somebody who was a Republican in their last seat. So they're going to try to overturn that seat. So that's something to realize as well. Another thing to realize here is that the reason why they're able to do regression discontinuity design is because they're actually going to look at different seats that are going to be overturned. So they're going to it's going to move from Republican to Democrat, Democrat to Republican by a very marginal percent. It's going to be within 2 percentage points. So the person that wins is going to win marginally. And what they argue in the paper is that this makes it as good as random who ends up winning, because both candidates had an equal opportunity or chance to win. So this is how they're kind of explaining their random assignment. Of course, looking at voters' share and who ends up winning is an endogenous problem, because it depends on the constituents' values and their desires and the specific events occurring during that time. So that's why they're using the regression discontinuity design and only focusing on the seats that were won marginally. So the first thing we're going to do is replicate table 1. Right, so let's go ahead and take a look. So this is the table we're recreating. Let's start with our first regression, which is going to be this one right here. We're going to regress the score of lag Democrat if the lag Dem vote share is greater than 0.48 and lag Dem vote share is less than 0.52. So remember, this is important. We're going 2% below the cutoff and 2% above the cutoff. So we're actually subsetting our sample to only be if the Democratic vote share was right below or right above. So basically, it's an exogenous random assignment, whether the Democratic representative won or the Republican representative won, if it's such a small, close marginal cutoff. So we get this 21.28 coefficient, which is what they get in the paper. And this represents the gamma here. So it's going to be this first figure. So this is ADA score time t plus 1, so the next election cycle, and this is Democratic vote share. So it's total effect of initial win on future ADA scores. So how does winning in the current period affect how liberal you're going to be in your political ideologies in the next period? So you can think about, for sequential games in game theory, if the politician wants their constituents to regard them as somebody that they can trust, that, if reelected, are still going to continue to have liberal ideologies in the next election cycle, then they are going to be scoring higher in ADA score, meaning they're going to have a more liberal score on in the future period. So this is the way you interpret this graph is saying that, look, if your Democratic vote share is below 50%, your ADA score, how liberal you are in the next period, is going to be here at around 25 or 30. But if you end up winning marginally right above the 50%, then your ADA score, how liberal you are, is going to jump. It's going to jump from around 25, 30 up to around 50. So it's going to jump 21 points. I guess that's what that gap looks like. So the measurement is showing that people who win marginally right above the cutoff to people who are right below the cutoff who didn't win, but they didn't win marginally, their future liberal scores are going to differ by 20 points for the Democratic candidate. So obviously that's not the case for Republicans, but if you're a Democrat and you're going to run for office again for the Democratic ticket, you have an incentive to have your second election, during your second election, to have greater liberal ideologies, because you feel that your constituents that voted you in the first time voted you in because of those ideologies. So it's actually going to create more divergence. So that was this regression, and we can use outreg2 to store it. Now let's go ahead and do the regression of Democrat if flag Dem vote share. Again, the same cutoff, greater than 0.48, less than 0.52. This one's going to be estimating this graph. This is Democratic vote share at time t and ADA score at time t. So this is not looking at the future period of being elected. This is looking at current time. Here the gap is actually larger. It's 20 and almost 70. So it's a 47-point gap. And that's what we see in table 1, 47.7. So what that means is if you win marginally right above the 0.5 mark, meaning your Democratic vote share was 51%, then there's probably your ADA score in the current period is probably much higher than if you were a candidate that was right below the cutoff. So it's just showing that the more liberal candidate ends up having greater Democratic vote share and ends up winning the election as well. And then this final one is a probability that a Democrat will win in the next election cycle based on the Democratic vote share of the current cycle at time t. T plus 1 is in the future, t is just the current period. And if we run that regression, we're going to be here. And we get 0.48, which is what they get in the table here. 0.48. As soon as you get to above 50%, 51% maybe of people are in the Democratic vote share, then the probability that Democratic will win in the next election jumps up a lot. But if you have less than 50% in the Democratic Party, then there's not a very high probability that the Democratic will win in the next election, which is what we expect. Here you have the elect component, here you have the effect component. If you can see here, the elect component is actually much stronger than the effect component. So that's why what I was mentioning earlier, it seems like voters elect rather than affect politicians and their ideologies. So now that we did that, let's go ahead and focus on using all of the data instead of just cutting it to the, here we're cutting it to the 48 to 52%. Now let's just look at all the data all together. Still clustered it at the ID level. One thing that I want to mention here is that we should probably outreg and append. So let me go ahead and actually run these. And then let me go ahead and reg this. And so here we're just using all of the data to see what our results would be. And now let's go ahead and look at if we have Democrat as our independent variable instead of lag Democrat. So remember, lag Democrat is the amount of voter share in the last period, whereas this is going to be in the current period. So we see 40. So if we look at the difference, here we get 31.5, here we got 21.2, here we got 47.6, here we're getting 40.7. So not very different. And then we're going to use Democrat and lag Democrat, which is what we did above. And we get 0.81 as opposed to 0.48. So this is where the big difference is in between just using the normal data, which is what we did here, the full set of data, versus if we constrain the data set to the subsample of the elections that barely got one at the cutoff. So basically, the main difference when we look at the full sample is that the probability that a Democrat will win in the next election cycle here is 48%, whereas here it's 82%. It's much higher. So it's important to only focus on the random assignment cases, the subsample where Democrats are barely winning. Otherwise, we're going to get this endogenous result that can't really be trusted. So now that we've looked at what the whole data looks like, this is the entire data. Let's actually recenter our data. So this is something that gets done with regression discontinuity design. We usually recenter the data based on the running variable. And the running variable here is vote share. How much of a vote share is going to each party. So here we're going to generate dem vote share. And we're going to put underscore C for cutoff. And we're going to say that the dem vote share, it's going to be the Democratic vote share minus 0.5. So remember, you have to get 50% or higher to win. So we're going to center it at 50% because that's our cutoff point. That's what we see in all of these figures. It's at 0.05. So you're going to want to subtract it at whatever your cutoff point is. Then we're going to run the regression of our score, the ADA score, with the lag Democrat and the dem vote share, underscore C for cutoff, clustered at the ID level. And then we're going to run the other regressions that we ran before. Democrat, we're just going to add dem vote share, underscore C, cluster ID, and then we're going to add reg Democrat. Yeah, reg Democrat, lag Democrat, dem vote share C, cluster at the ID level, and let's see how that goes. So let's first generate this. Okay, so we can see what it looks like. So we just took the dem vote share and we subtracted it by 0.5. So let's actually order dem vote share and then dem vote share underscore C to the front to see what happened. So this just got subtracted by 0.5. So like here we're left with 0.05. So that's the Democratic vote share at the cutoff, right? So if we're recentering it, we don't want it to be 0.55, right? We want it to see how much above or below you are to the cutoff. So here, this person was marginally right above the cutoff. They were 0.053 above. Here, this person was negative 0.03. So that means they were right below the cutoff. They didn't quite make it. They were almost there. So basically, we're trying to figure out how close were people to the cutoff. Because remember, we're only looking at people who barely won or barely lost. We don't want to focus like people like this. I mean, this is a false example because the Democratic vote share, well, actually, it's not false. The Democratic vote share was 0. So basically, everyone in this district voted for Republican, so we don't want this kind of person to be in the sample, right? Or this ID to be in the sample. That's why it's important to make that. So now let's do our regressions using the regression score, lag Democrat, and Dem vote sure with the cutoff. And we get 33.45. And the Dem vote sure cutoff, the coefficient is negative 5.6, and it actually is statistically significant. Let's see if this is a table replication. So results based on nominate close selection sample. We're still using the whole sample here. So it doesn't look like this is replicating a table, but rather just looking at what happens when you add the cutoff point. So let's go ahead and keep going on with this. So now let's do the score with the Democrat. So it's the same model as this one. We're just adding the cutoff point now. So Dem, let's try that again. Okay, so here you get 58.5 is the Democrat coefficient, but the Democrat vote sure cutoff gives you negative 48. And here you get 0.55, and the Democratic vote sure is 0.77. So if we want to compare this to table 1, we would see that we're pretty close, but still a little bit far off for the coefficient. So once you add a coefficient that explains how close or far you are to the cutoff, you're seeing that the lag Democrat is 33, which is close, but still not quite there. And then you're seeing that the second one, which is the ADA, the pi, that's 47.6, which is, this one's 58.5, close but not there. But here, this got better, right? When we used the whole sample and we didn't have the cutoff, we were at 0.8, which is really high compared to 0.48. Now that we've added the cutoff, how close or far you are from, winning or losing the election, getting above 50% or below, you get pretty close to what it looks like when you have a subsample, when you had this initial estimation here. So we're getting better. Now let's go ahead and after we've done recentering the data, let's use all the data but interact the treatment variable with the running variable. So here I'm going to use this xi. Xi just means if I haven't created this variable already in my data, just create it while I'm on the fly running the regression. So for instance, the interaction variable, it doesn't exist in my exist in my data. So when I put xi here, it's going to create the interacted variable for me in case I want to look at it, make sure it's being done right, or use it later on. So now I'm going to do i.lag Democrat, and I'm going to multiply that by Dem vote share at the cutoff. I'm going to cluster the ID. Okay, now we're at 30.5. Still close. Now let's do the second regression specification, the Democrat times Dem vote share. Clustered at the ID level. And then finally, let's do Democrat as the dependent variable. So remember the one that's the probability that you will be that a Democratic politician will be voted in the next election cycle based on Democratic voter share. So here we're interacting our running variable and our treatment variable, and we get 0.525. So close, but still not quite where we wanted to get when we had subsampled. But as you can see, our Dem vote share actually now has a positive sign, whereas before when we ran it, still positive, still statistically significant, but now Dem vote share cutoff has more of a economic significance. It's increased by a little bit. And just to remind you, when you see an _1 here, so this is the interaction of the two. Lag Dem times the Dem vote share. So now, let's go ahead and look at our next thing. We went ahead and ran the regression with the interaction of the treatment variable and the running variable. Let's go ahead and do some other specifications for robustness checks. Let's go ahead and use all the data again, but interact the treatment variable with the running variable like we did before, and a Quartic root, which just means that we're going to be squaring it. So gen dem vote share square is going to equal to dem vote share at the cutoff that we just made, and we're going to square it. We use the xi again because we're not going to have these variables created. We want Stata to create them for us. And another way to do interactions, if you don't want to type out each individual term that you want it to include in the model, like let's say we want lag Democrat, and we want on top of that Dem vote share cutoff, and we want the interaction between the two, meaning the multiplication, we can use this double hashtags. And if we write C here, C just stands for it's going to be a continuous variable, and we're going to put in parentheses Dem vote share at the cutoff and Dem vote share squared that we just made. And we're going to cluster at the ID level. So here we're actually multiplying lag Democrat with Dem vote share at the cutoff, as well as with Dem vote share squared. So first we have to run this one. So that got created. Here is the Dem vote share squared. Now let's run the regression. So remember I said that when you use the double hashtag or the multiplication, you're just creating new variables. So we can probably actually see them here. Dem vote share squared. And it doesn't look like it's creating those variables. That's okay. But here we can read it, right? So when you see a 1 here, that means that lag Democrat had to be equal to 1. So anytime you have an I dot, it's just saying that's an indicator. Here, lag Democrat is actually a 0-1 dichotomous. So when lag Democrat is equal to 1, multiplied by the continuous variable Dem vote share at the cutoff, the coefficient is 57.05. And remember, when you're working with a dummy variable interaction, you're always comparing it to the time when the dichotomous variable is equal to 0. So this coefficient is in reference to when lag Democrat equals 0. So in the last seat in that position in the Senate or the House of Representatives was not a Democrat, meaning it was held by a Republican, it'd be equal to 0. So this coefficient can be interpreted as when there was a Democratic representative in the last cycle present, multiplied by whatever the Dem vote share is, the impact on this ADA score is going to be 57.05 compared to when in the last election there was a Republican. So remember, you have to compare it to when lag Democrat equals 0. So when we add the squared term, we get 57.05 for our Democrat times Dem vote share, which is our first model, and we see that it's different from what we got here, the 21.2. So let's go ahead and keep going, right? We would expect it to be different. So let's try xi reg score Democrat. Double hashtag means, remember, we're multiplying, but we're keeping the Democrat term, the second term, which is going to be C dot Dem vote share and Dem vote share squared. So we're keeping Democrat, this one, and this one, but we're also keeping the interaction, right? So here they came in separately, log Democrat, Dem vote share squared, but we also had the interactions. So instead of having to type everything out, the double hashtags are pretty helpful. And here we see Dem vote share, Democrat times Dem vote share is 111. Here it's negative 229. Here the coefficient is 44. So if we compare this one, we're at 47. So we're actually right below. So when we add a quartic root, so meaning we're squaring the Dem vote share cutoff, we add that into our sample, and we do an interaction between the treatment variable and the running variable with that quartic root, we end up that our lag Democrat, which is our main variable of interest for the first one, is right below, right? It's 13, but it's supposed to be 21 as according to the table. 47, but here it's 44. So let's see how our third regression fares. So if we do this one, xi reg Democrat, lag Democrat, C dot Dem vote share at the cutoff, and then Dem vote share squared. So we're going to interact both of those. So remember, it's lag Democrat getting multiplied by this one separately, and then lag Democrat getting multiplied by this one separately. So this is the probability that in the next election cycle you're going to be voted a Democrat based on the Democratic voter share. And here we see it's 0.32. And here it was 0.48, so it's still below. So we see that these estimates are right below the estimates that we found on the paper. And basically what it's proving is that we did all these different specifications, right? These robustness checks, kind of. And it's just proving that the effects that we see here, this first column and this column and the probability, these are persistent effects. These effects are truly present for the competitive races where candidates don't change their policy from pre-election. So in the cases where candidates are not changing their policy from before they got elected. The voter share, the turnout, the probability of getting re-elected next year, it's pretty persistent regardless of what kind of specification we put, even when we add this quartic root thing. So that's good, right? We want that. Now let's go ahead and use 5 points from the cutoff. So let's go ahead and do reg score lag Democrat multiplied by dem vote share underscore C dem vote share squared. Let's do if lag dem vote share is greater than 0.45 and lag dem vote share is less than 0.55. Let's cluster at the ID. So remember up here we used only 0.2 above and below. Here we're opening up the window to be 5 above and 5 below. It doesn't like something here. Let's try this instead. So that worked, right? So here we see when we add the window to be bigger, this is actually even smaller than before. The estimated gap is 3. Now let's do the second specification. That's going to give us the pi coefficient. It's going to be the same thing as up here, so we can just copy and paste this part. So if we run this, we're going to be at 46.87. So it's right pretty close to the 47. And the last one we can just copy and paste this. Which shows 0.118. Okay, so now we see the probability that a Democrat will get elected in the next period if their vote share is above the cutoff within 5%. Actually goes down, right? The probability is 0.118. So basically what this is showing is that you don't want to look at too big of a window, right? You don't want to look at the effect 5% out on each side. It's actually important to only focus our subsample within 2% up and below, because that's going to give us our random assignment coin flip that, you know, it's just about random who ends up getting elected, whether it be Republican or Democrat. If you see 48%, it's almost random whether a Democrat or Republican is going to be elected next time. It's only 2% off. So that's what kind of gives us our random assignment here. So 5% is too big of a window. We should stick with looking at 2%. So now let's go ahead and run some of our histograms. This is going to give us these pretty plots that we see in the paper for the RDD design. So let's run some non-parametric histograms from the cutoff. So if you guys don't have this on your machine already, go ahead and SSC install Semogram. I don't think I do because this is a new laptop. And our first picture is going to be using the score and then our lag dem vote share. The cutoff, remember, is going to be 0.5. And we want a scatter and a line plot. Sorry, a scatter plot and a line at 0.5 to show the cutoff. And we want an L fit, which means we're going to do like a local linear fit. There's some other options. You can do a Loess regression as well. You can do a Q fit. So you could do different fits depending on what kind of kernel you're going to use for your model. So if we're going to use a linear, local linear kernel, then we can use L fit. So here's our graph. So our lag dem vote share is our running variable, right? And then the average ADA score is here. And then this is what it looks like. So it may not look like a big jump, but look at the scale here. It's 15 to 70. So this is at about maybe 20. This is at 60, so it's almost a 40-point split here. So remember, this one was the lag dem vote share and the score. So this is going to be like our first regression that we started, score and lag democrat. It's going to be this one here. Sorry, this one here. So it should be, yeah, right above 20. And then right there at 60, which is what we see. And you see these lines here? It's doing a line because we said L fit, which means linear fit. Here they don't have a line, right? There's kind of a little bit of a curvature because maybe they chose a quadratic fit. So that's something to kind of note here. Let's try a different fit on our graph. So let's do the same graph, like dem vote share. The cutoff is at 0.5. Scatter, line, 0.5. Let's try Q fit instead. Okay, so now we get a pretty good fit, quadratic fit here. It's fitting the data pretty well, and we got confidence intervals around it too. So the gray lines are the confidence intervals. But you see how it's actually doing a pretty exact fit, like it doesn't capture any of these dots. Whereas here it's actually capturing the dots, so that's something to notice. So it's actually a pretty tight fit that's going on with the Q fit. Let's try a different one. Let's try a Loess fit. So the Loess function. Okay, so here I would actually argue that maybe this is more of a strict fit than the last one, right? The last one kind of just did a quadratic. It tried to basically plot quadratic functions on the data. This one is just trying to plot as many points as possible given the same trend. We can see that here. If you want to look at different options, you can do help semogram to see what other options there are. So L fit is a plot a line of best fit. LT fit CI is the same as L fit but with confidence intervals. Q fit is the same as L fit but with quadratic. We did the Q fit CI. Loess plots a local linear smooth. So you actually typically see a local linear plot when you see these. Here it looked like the quadratic fit was the best though. So we can actually also do the same one, but with the confidence interval. So again, just to go through them, this is when you have a linear fit. It just draws a line of best fit. Here is the linear fit with confidence intervals. Not all the dots fall in the confidence intervals, so I would argue that's not the best one. Here you got the quadratic fit with the confidence intervals. And now you've got the lowest function, which is the local linear fit. That's getting computed right now. So that's how you draw these graphs. We can also draw a local polynomial model. So let's go ahead and try that. We use the L poly. So let's actually just say we're going to do local polynomial model. So we're going to do L poly score dem vote share if Democrat equals 0. No graph. Kernel is going to be a triangle. Gen x0. SDM0. And then we can do bin width, so we can do all these extra different options as well. Doing the local polynomial model, we're just trying to take our other models that we did the semogram and kind of smooth the function out. So when we're running this model, it's actually known to smooth the function out because it's going to be a kernel weighted function. So kernel weighted local polynomials are going to smooth the function out. And so here we're doing the local polynomial if Democrat equals 0. So that means you're not a Democrat. And then here it's Democrat equals 1. We're setting the kernel to be a triangular kernel because that's what seems to fit our data best. We're generating these variables so that afterwards we can run a scatter plot with them using the generated values that we created. Let's go ahead and run that. So x is already defined because I ran this function already. So let's run the scatter plot. So this is what we get. So this is when dem vote share is equal to 0. This is when it's equal to 1, right, at the cutoff. So we see a difference of about 40 points here in ADA score when the Democrat vote share gets right above the cutoff. So remember, we had found this before. It's right here. Same as this plot right here. And it's at time equals t. That's why you don't see a lag. So now let's go ahead and try to test robustness of our coefficients. So if you don't already have this downloaded on your machine, go ahead and put in SSC install rdrobust. Now let's run the rdrobust function with score and dem vote share. Remember the cutoff is 0.5, so we should note that. We need to let that load though. I will mention here that when we're checking for robustness and bias, we're going to see different coefficients. Because as we compare the different standard errors and variances or variance controls, the bin sizes will change. By the approach, and that's going to impact the coefficients. So the idea here is that the bin size is just the window that we're looking at. We're going to look at 50% left and right, 2% left and right. So as that changes, it's going to have a slight impact on the coefficients. Here we get our RD robust coefficients. Remember, these are robustness checks. That we're doing. So it says that we're using a sharp RD. Remember in class you learned there's also a fuzzy RD. This is sharp cutoff though. This is the number of observations to the left of the cutoff. This is to the right. And here's our outcome score, running variables the Democratic vote share. And we get 46.49. Now, another important thing to do when you run an RD is you want to look at a McCrary density test. So this basically is saying that there shouldn't be any big changes or discontinuities at the threshold. Your density should be the same. Otherwise, there may be manipulation going on. People may be self-selecting into the preferable treatment or getting out of treatment if it's not desirable. So the density test just makes sure that there's no people aren't able to, manipulate their score into treatment. So when we're looking at the for in this scenario, when we're looking at the vote share and people winning by a marginal 2%, we just want to make sure there's no manipulation happening at that 2% mark, that it's as good as random, that one party wins versus the other party winning if it's a marginal election. So to run a McCrary density test, and another way to kind of just summarize what I just said is that we're checking to see if there's bunching at the threshold. So you're going to want to actually install this from the net. So sometimes you have to net install things that aren't in Stata's packages locally from their computer anymore. So we're going to actually install it from this website on GitHub. Change the link here and hopefully this one works. I recommend to copy and paste it onto this command window. It worked fine for me. So here you can see the failed link. Here you can see the one that works. I'm not going to run it again because it took a little bit of time and it actually crashed my laptop for a second. So I'm going to move on to the next net install that you have to do for the local polynomial density plot. So that one's running. So remember, net install just means it's going to the internet, to the website you plugged in there, and it's going to install the package from that website. Now there's going to be this last DC density command. That one doesn't have a website here. Actually, if you go to Canvas, I have the dcdensity.addDo file, and I'll show you where you can save that. So just go ahead and download that onto your laptop. So let's first run this RD density command. So here, remember, we're doing the McCrary density test. And remember here, we don't want to see, if manipulation is occurring, right, then you're going to see that this side is going to be at 0, and then it's going to shoot up to 1. So there's going to be a huge gap. Here we're not seeing that huge gap. There's a small gap, but that's expected. If we saw a huge gap here, then we would be able to tell that there's manipulation going on. If you look at the scale here, that's a gap of like maybe 0.02 or something like that. So it's very small. So that checks out. We don't have manipulation going on. People are not choosing to be in one Democratic vote share for a specific reason to manipulate their score. So basically, politicians are not acting more liberal in certain circumstances to manipulate their score, and that's what we can see in that plot. Now remember, the DC density command is different, right? That one, you're going to have to download on Canvas the addDo file. This is what it looks like. So this is what the program is going to be doing. So when you call for DC density, this is the code that actually gets ran. You don't need to know any of this. This is just the background code. Just open up the do file, go to File, go to Save As. Now it's important where you save this. So you're going to want to go to wherever you put your applications. And then you're going to want to look for Stata in your applications. Once you get to Stata, you want to go to the addDo folder. And then you want to pick D for density. And then you want to save it there, DC density. Okay, so you have to save it in the addDo folder for the function to work. So once you've done that, you should be able to run this DC density function, okay? And this is looking at discontinuity estimate. Log difference in height is 0.011. 0.06 p-value, so it's not statistically significant. So this is another plot that's showing that there's no significant discontinuity. So remember the RD density plot. That one made it look like there was somewhat of a discontinuity, but remember I said it was so small that it's not significant. So that means that there's no manipulation going on. Here, we're able to confirm just call it KJ. Let's just call it KXI. YI. PO. T hat. T hat. Let's try doing this. Right, so here it's actually looking like there is no jump at the cutoff. So we're basically showing that there's no manipulation going on. People are not choosing on purpose to be in the treated group or the untreated group. They're not choosing to be assigned treatment. So it's all happening randomly. So remember with RDD, it's very important that you have random assignment. So that concludes the replication of the paper. Just overall some tips. When you run an RDD, pick a running variable, which is the variable that is on the x-axis, not in this plot, but in the other plots we looked at, such as this one. The running variable here is democratic vote share from the AD. Yeah, the democratic vote share. So pick a running variable that you would predict has a discrete cutoff if you're going to do a sharp RDD. So here the discrete cutoff is 0.5. If you think it's going to be not discrete cutoff, but instead of there being an exact jump, but maybe a probability from going from low to high, then you're going to be in the fuzzy RDD range, not the discrete. And make sure that you don't have you shouldn't have any jumps for the control variables. So if you're looking at in your models white, male, population, you should see no jumps at the breakpoint. And 2, you don't want your McCrary density test to show bunching. Basically, you don't want there to be any kind of jumps there. You want it to be continuous. Otherwise, you have manipulation going on with the density. So those are the 2 things you want to check when you're doing RDD. If you're doing those things right, more than likely you're looking at an exogenous scenario, which is what you want. And you're all set then. So this is Asynchronous Learning Module 8. Please feel free to reach out to Uni or I if you have any questions or concerns with this. And good luck, guys.